I want to start with a number. Not an abstract number, not a placeholder, but a specific measurement made by a specific instrument pointed at a specific patch of sky over a specific number of hours. The number is 13.8 billion. That is the age of the universe in years. You have heard this number before. It appears in every cosmology textbook, every documentary, every popular account of the Big Bang. It is the number we reach when we run the expansion of the universe backward in time to the moment of maximum density. 13.8 billion years. The universe is old, but I want to use that number to arrive at a second number that most people have not heard, and that most people, when they hear it for the first time, find genuinely disturbing. Not abstractly disturbing in the way that all large numbers are hard to grasp, viscerally disturbing in the way that makes the ground feel less solid and the sky feel less bounded, and the comfortable assumption that we understand where we are feels suddenly specifically wrong. The second number is 93 billion. That is the diameter of the observable universe in light years. Not 13.8 billion, which would be the diameter if light had simply been traveling since the Big Bang in a static space. 93 billion light years, 2.5 times larger than the time light has had to travel since the beginning. The universe is nearly 7 times older than the light that fills it. Or rather, the universe has expanded so much since that light was emitted that the sources of that light are now 6.5 times farther away than the light has had to travel. This number is the first thing James Webb has sharpened for us. Not changed, not revised upward, not discovered, sharpened, made precise, made real. Webb has looked further into the universe than any instrument before it, and what it has seen is not a boundary, not an edge, not a wall. It has seen galaxies at the very limit of what the age of the universe allows us to see, and those galaxies are receding from us so fast that the light from them has been traveling for 13.4 billion years and arrived at Webb's mirror with a wavelength stretched to 14 times its original length by the expansion of the space it crossed. What James Webb has done is not just measure. It has made the size of the universe something you can look at, something you can confront with an image rather than a number. The deep field images from Webb, the photographs of thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length, each galaxy containing hundreds of billions of stars, some of them existing when the universe was less than 500 million years old, are not abstract data. They are the universe showing you how large it is, and the size is terrifying. I want to take you through what Webb has actually found, what the measurements mean, why the true size of the observable universe is larger than the age of the universe would suggest, and what lies beyond the observable edge. Because beyond the 46 billion light years of the observable universe, there is more, much more, possibly infinitely more. And the ratio between what we can see and what might exist is a number that makes 93 billion look small. Let me start with what James Webb is and why it can see further than anything before it. The James Webb Space Telescope is the largest, most powerful, and most precisely engineered space telescope ever built. It has a primary mirror, 6.5 meters in diameter, made of 18 hexagonal segments of beryllium coated with gold, designed to reflect infrared light with extraordinary efficiency. It was launched on the 25th of December, 2021, and reached its operating position at the L2 Lagrange point 1.5 million kilometers from Earth in January 2022. It began science operations in the summer of 2022. The James Webb Space Telescope is the largest, most powerful, and most precisely engineered space telescope ever built. It has a primary mirror 6.5 meters in diameter, made of 18 hexagonal segments of beryllium coated with gold, designed to reflect infrared light with extraordinary efficiency. It was launched on the 25th of December 2021 and reached its operating position at the L2 Lagrange point, 1.5 million kilometers from Earth, in January 2022. It began science operations in the summer of 2022. Let me describe what makes Webb fundamentally different from what came before, because the capabilities are not just quantitatively better, but qualitatively different in ways that determine what it can see. The Hubble Space Telescope, launched in 1990, operates primarily in optical and ultraviolet wavelengths, the wavelengths of visible light and the shorter wavelengths just beyond the violet end of the spectrum. Hubble's primary mirror is 2.4 meters in diameter. For 3 decades, Hubble was the defining instrument of observational astronomy, producing images of galaxies, nebulae, and planetary systems with a clarity that ground-based telescopes, limited by atmospheric turbulence, could not match. Webb's primary mirror, at 6.5 meters, collects approximately 7 times more light than Hubble's. This alone makes it far more sensitive. But the decisive advantage for early universe science is not the mirror size, it is the wavelength range. When astronomers describe the light they observe from distant objects, they use the concept of redshift, the stretching of light wavelengths by the expansion of space during the journey from source to detector. A redshift of z equals 1 means the wavelengths have been doubled. A redshift of z equals 9 means they have been stretched to 10 times their original length. For a galaxy at redshift z equals 9 whose starlight was originally emitted at wavelengths of 100 to 400 nanometers, the observed wavelengths at Earth are 1,000 to 4,000 nanometers, the near infrared. Hubble is largely blind to these wavelengths. Webb is optimized for them. Webb detects light in the range from 0.6 to 28 micrometers, covering the near-infrared and mid-infrared. This range was chosen specifically to see galaxies in the first billion years of cosmic history. The instrument suite includes NIRCam, the near-infrared camera that produces the extraordinary deep-field images, NIRSpec, the near-infrared spectrograph that can observe up to 100 galaxies simultaneously and measure their redshifts, star formation rates, and chemical compositions, MIRI, the mid-infrared instrument that detects the coolest and most dust-obscured objects, and FGS, NIRIS, the fine guidance sensor and near-infrared imager used for target acquisition and additional science. To operate at these infrared wavelengths, Webb must be colder than minus 233 degrees Celsius, just 40 degrees above absolute zero. Any thermal radiation from the telescope itself would overwhelm the faint infrared signals it is trying to detect. Webb achieves this temperature using a 5-layer sunshield the size of a tennis court, which keeps the telescope permanently shadowed from the sun, Earth, and Moon. The engineering required to fold this shield into the rocket fairing, deploy it in space, and maintain the precise temperature gradients needed is among the most complex ever undertaken in the history of space exploration. The deployment of Webb after launch was the most stressful sequence of events in the history of space telescopes. 344 single-point failure mechanisms had to work correctly in sequence over the month following launch. The mirror segments had to unfold and align to within nanometers of precision. The sunshield had to deploy and tension correctly. Every step was irreversible because Webb is too far from Earth for astronaut repair missions. When everything worked, the relief among the thousands of engineers and scientists who had worked on the project for more than 2 decades was visible in every press conference. Webb's most critical capability for the purpose of seeing the early universe is its sensitivity to infrared light. Light from the earliest galaxies has been traveling for more than 13 billion years. During that journey, the expansion of the universe has stretched its wavelength by a factor of 10 or more, shifting it from the optical and ultraviolet wavelengths at which it was emitted into the infrared. Hubble could not detect this redshifted light efficiently. Webb designed from the beginning to see in the infrared, can detect light that left its source when the universe was only a few 100 million years old. The specific capability is measured in terms of redshift. A galaxy with a redshift of z equals 1 has had its light wavelengths doubled by the expansion of the universe during the journey. A redshift of z equals 2 means the wavelengths have been tripled. A redshift of z equals 10 means the wavelengths have been stretched to 11 times their original length. The look-back time for a galaxy at redshift z equals 10 is approximately 13.3 billion years, meaning the light we are receiving was emitted when the universe was approximately 500 million years old. The Hubble Space Telescope could detect galaxies reliably up to redshifts of about z equals 10 or 11 with great difficulty and long exposure times. James Webb can detect galaxies at redshifts above 13, and in its first year of operation found several candidate galaxies at redshifts above 16, meaning the light was emitted when the universe was only about 250 million years old. The galaxy currently holding the record for highest confirmed redshift as of mid-2024 is JADES GSZ. 14 minus 0, confirmed at a redshift of z, equals 14.32. This means the light arriving at Webb's mirror from this galaxy was emitted when the universe was approximately 290 million years old. The light has been traveling for 13.5 billion years. The galaxy is, at this moment, approximately 33 billion light years away from us because the universe has expanded while the light was traveling. These numbers are not the point. The point is what they imply. When Webb looks at JADES GSZ 140, it is looking at a galaxy that existed when the universe was less than 3% of its current age. The Sun had not yet formed. The Milky Way had not yet formed. The heavy elements needed for rocky planets had not yet been produced in significant quantities. And yet, there was already a galaxy, already containing hundreds of millions of stars, already showing the signatures of ongoing star formation. A galaxy that had no right to exist so soon after the Big Bang by the standard models. A galaxy that is forcing us to revise those models. But I want to step back from the individual record breakers and describe what Webb has revealed about the distribution of galaxies across the observable universe, because the picture that emerges is more disturbing than any individual measurement. In 1995, the Hubble Space Telescope pointed at a patch of sky in the constellation Ursa Major, a region that appeared completely dark in previous surveys, containing no known stars or galaxies. It stared at that patch for 10 days. The resulting image, the Hubble Deep Field, showed more than 3,000 galaxies in a patch of sky with an angular area of 1 square arc minute, smaller than a grain of sand, held at arm's length. In every direction, in every apparently empty patch of sky, there are thousands of galaxies. Let me put the density of galaxies in the deep field images into a concrete perspective, because the numbers require some anchoring to be felt rather than merely heard. The patch of sky covered by the original Hubble Deep Field is approximately 5.3 square arc minutes. The full sky contains approximately 148,510,660 square arc minutes, dividing and multiplying. If the galaxy density of the Hubble Deep Field is representative of the full sky, which it appears to be in the infrared, where obscuration by dust in our galaxy is minimized, then there are approximately 3,000 galaxies in every 5.3 square arc minutes of sky, or roughly 560 galaxies per square arc minute, or about 83 billion galaxies visible in the full sky with Hubble's sensitivity. With Webb's greater depth, reaching fainter and more distant galaxies, the count increases. The current best estimate is 2 trillion galaxies in the observable universe, a factor of 10 larger than the previous estimate of 200 billion. Most of the additional galaxies are small, faint, distant, and were simply below the detection threshold of previous surveys. 2 trillion galaxies, each containing an average of 100 billion stars. That gives 2 times 10 to the 23rd stars. Let me try to give this a human scale reference. If you were to count 1 star per second, every second of every day, with no breaks, it would take approximately 6 trillion years to count all the stars in the observable universe. The universe is 13.8 billion years old. You would need to count for 400 times the current age of the universe just to number the stars. If you were to travel to each star at the speed of light, 1 per second, the journey would require 6 trillion years. By the time you finished, the last stars in the universe would be going out. The stellar era of the universe would be over, and you would have visited 1 star per second the entire time. Another way to grasp the scale, the observable universe contains approximately 10 to the 80 atoms. Every cubic meter of space in the observable universe, averaged across its volume, contains approximately 1 atom. The density of matter in the observable universe is about 1 proton per cubic meter. That is how dilute the universe is. And yet the total number of atoms is 10 to the 80 because the volume is so incomprehensibly large. A spoonful of water contains approximately 10 to the 25 molecules of H2O. Each molecule contains 3 atoms. So a spoonful of water contains roughly 3 times 10 to the 25 atoms. The observable universe contains approximately 10 to the 80 atoms, which means the observable universe contains the same number of atoms as approximately 3 times 10 to the 54 spoonfuls of water. A number so large, it would fill the observable universe itself with water more than 10 to the 24 times over. These numbers are not meant to impress. They are meant to make viscerally clear that the scale of the observable universe is not just large in the way that continents and oceans are large, where we can traverse them in days or weeks. It is large in a way that no human experience, no analogy, no metaphor can fully bridge. The observable universe is not large. It is incomprehensibly, unimaginably, terrifyingly large. And it is the small part. In 1995, the Hubble Space Telescope pointed at a patch of sky in the constellation Ursa Major. The Hubble Ultra Deep Field, taken in 2003 and 2004, extended this to an even smaller patch, revealing approximately 10,000 galaxies in an area of 1/30th of the Moon's diameter. The images showed galaxies at every stage of evolution, from mature spirals and ellipticals to the tiny irregular blue smudges of the earliest galaxies Hubble could detect. James Webb pointed at the same patch. The James Webb Deep Field, released in July 2022, the first science image released by the mission, showed the same region with infrared sensitivity that Hubble lacked. Webb's image revealed galaxies that Hubble had not detected at higher redshifts at earlier cosmic epochs. And it showed them with a clarity and resolution that revealed structure within individual galaxies that had appeared as blurs in the Hubble images. But what the deep field images collectively reveal is not just the existence of many galaxies. It is the density of galaxies across the observable volume. Extrapolating from deep field surveys to the full sky, the observable universe contains approximately 2 trillion galaxies. 2 trillion. The estimate was revised upward by a factor of 10 from the previous estimate of 200 billion when deeper surveys with Hubble and now Webb revealed that many small, faint galaxies had been missing from earlier counts. 2 trillion galaxies, each containing an average of perhaps 100 billion stars. The total number of stars in the observable universe is approximately 2 times 10 to the 23rd power, which is a number larger than the number of grains of sand on all the beaches and deserts of Earth. For every grain of sand on Earth, there are 10,000 stars in the observable universe. Now let me take you to what happens when you try to understand the actual physical size of the space that contains all of this. The observable universe has a radius of approximately 46 billion light years. This is the moving radius, the distance to the most distant objects we can in principle observe. Accounting for the expansion of the universe, the diameter is approximately 93 billion light years. Why is this number larger than 13.8 billion light years, the number you would expect if the universe were simply the region that light has had time to reach since the Big Bang? The answer is the expansion of space. When the light we are now receiving from the most distant galaxies was emitted, those galaxies were much closer to us than they are now. The universe was smaller. As the light traveled toward us, the space between us and the source was expanding. The source was being carried farther away by the expansion. By the time the light reached us, after 8 billion years of travel, the source had been carried to a position 46 billion light years away. The space the light crossed during its journey was not a fixed 46 billion light years. The space was expanding as the light crossed it. The light traveled 13.8 billion light years in the sense that it has been traveling for 13.8 billion years at the speed of light. But it crossed a moving distance of 46 billion light years because the space it was crossing was expanding during the journey. This is the expansion of space I described in the previous video about what the universe is expanding into. The 93 billion light year diameter of the observable universe is the direct consequence of the expansion of space during the 13.8 billion years since the Big Bang. James Webb has now imaged galaxies at the edge of this observable volume, not at 13.8 billion light years, at 33 billion light years, at redshifts where the light was emitted so long ago that the source is now near the limit of what the expansion allows us to see. Webb has pushed the observable frontier as close to the theoretical edge as any instrument has come. And what it has found at the edge is not emptiness, it is more galaxies, more structure, more complexity. The universe does not become sparse as you approach the observable limit. The galaxies continue, as numerous and as complex as those nearby, up to the very edge of what the age of the universe allows us to see. Which brings me to the question that I think is the most genuinely disturbing aspect of what Webb has revealed. Not what is at the observable edge, what is beyond it. The observable universe is not the universe. It is the part of the universe that is observable from our location. The observable universe is a sphere centered on Earth, defined by the maximum distance that light has had time to reach us from since the Big Bang. Beyond that sphere, there is more universe. The question is how much more? The current best estimate from the Planck satellite's measurements of the cosmic microwave background is that the total universe is at least 23 trillion light years across. This is a conservative lower bound. The actual universe could be much larger. It could be infinite. Let me explain where the 23 trillion light year lower bound comes from, because it is not obvious. The CMB measurements show that the universe is very close to flat, meaning its geometry is consistent with Euclidean geometry on the largest scales. If the universe were positively curved, like the surface of a sphere, the total volume would be finite, and the curvature would manifest as specific distortions in the CMB power spectrum. If the universe were negatively curved, like a saddle surface, it would also be detectable. Planck measured the curvature parameter omega to be equal to 1 within approximately 0.4%. This means if the universe is curved, the radius of curvature is so large that its effects are below the threshold of current measurement. For a sphere with curvature just below the Planck detection threshold, the circumference would be at least 250 times the diameter of the observable universe. The total volume would be at least 250 cubed, or approximately 15 million, times the volume of the observable universe. With 15 million times the observable volume, the total universe would contain at least 30 quadrillion trillion galaxies if the galaxy density is uniform. Numbers that are meaningless except in their demonstration that the observable universe is not the universe. But the strongest argument for a large or infinite universe comes not from the CMB curvature measurement, but from inflationary cosmology. In the inflationary picture, the universe underwent a period of extraordinarily rapid exponential expansion in the first fraction of a second after the Big Bang. The inflation stretched quantum fluctuations to macroscopic scales and produced the density variations that seeded all the structure we observe. It also smoothed out any initial curvature, driving the geometry toward flatness. The specific model of inflation that best fits the CMB data predicts a universe many orders of magnitude larger than the observable part. In eternal inflation, a specific class of inflationary models, inflation does not end everywhere simultaneously. In most regions of space, inflation continues forever. In rare quantum fluctuation events, inflation ends locally and a region stops inflating and begins evolving as a conventional Big Bang universe. Our observable universe is one such region, one bubble of non-inflating space within an eternally inflating background. In eternal inflation, the number of bubble universes that have formed is unbounded. The eternally inflating background keeps producing new bubbles, each a new Big Bang, each with potentially different initial conditions and physical constants. The total number of bubbles is infinite. The total volume of the multiverse is infinite. Our observable universe is an infinitesimal fraction of what eternal inflation predicts to exist. This is the sense in which the true size of the universe is not just unknown, but unknowable in principle. If eternal inflation is correct, the total universe is not just large or very large or incomprehensibly large. It is infinite in extent, containing infinite numbers of galaxies, infinite numbers of stars, infinite numbers of planets, and the logical consequence of infinite space with finite possible quantum states, infinite copies of everything, including you. The distance to the nearest exact quantum state copy of you in an infinite universe with the observed density is approximately 10 to the 10 to the 28 meters. Written out, 10 to the 28th power is a number with 28 zeros. 10 raised to that number is a number so large that writing it out would require more digits than there are particles in the observable universe. The nearest copy of you is that far away. James Webb has not changed this picture of the total universe. What it has done is sharpen our understanding of the observable universe, of what exists within the 46 billion light-year sphere we can access. And what exists is extraordinary enough. 2 trillion galaxies, 2 times 10 to the 23rd stars, the full history of cosmic evolution from 290 million years after the Big Bang to the present, all contained within a sphere that is itself only a tiny fraction of the total universe. Now let me take you to what Webb has found that is specifically new, that was not known before Webb began operations, because I do not want this video to be simply a description of what was already understood. Webb has produced genuinely surprising results that are forcing revisions to the standard model of cosmology. The most significant is the problem of massive early galaxies that I described in the video about James Webb and the Lambda-CDM tension. Webb has found galaxies in the first few hundred million years of cosmic history that are more massive than the standard model of galaxy formation allows. The standard model, based on the Lambda-CDM cosmology, predicts that galaxies grow hierarchically, starting from small clumps of dark matter and gas that gradually merge and accrete into larger structures. Massive galaxies should not exist in the very early universe because there has not been enough time for the hierarchical assembly to build them. Let me describe the specific mechanism of galaxy formation in the Standard Model, because understanding it makes the early massive galaxy anomaly precise rather than vague. In Lambda-CDM, the universe is dominated by cold, dark matter, which clusters under gravity from the small density perturbations seeded by inflation. The dark matter halos, gravitational potential wells form hierarchically. Small halos form first, then merge into larger halos. The ordinary matter, hydrogen and helium from Big Bang nucleosynthesis, falls into these dark matter halos, cools by radiating energy, and forms stars. The first galaxies are small because the first dark matter halos are small. The hierarchical assembly process takes time. To build a galaxy with a stellar mass of 10 to the 11 solar masses, comparable to the Milky Way, the Standard Model requires roughly 2 to 4 billion years of merging and accretion. Galaxies of this mass should not exist in the first billion years. The specific signature that allows Webb to measure galaxy masses at high redshift comes from its near-infrared spectrograph. Starlight is dominated by the most luminous stars, which are hot and blue, but the total stellar mass is dominated by the less luminous, longer-lived stars, which are cooler and redder. To measure a total stellar mass, rather than just the luminosity, astronomers need to detect the near-infrared emission from the cool stars. For galaxies at high redshift, this near-infrared emission has been shifted to even longer wavelengths into Webb's mid-infrared range. Webb can detect it where Hubble could not. In the first year of operations, Webb found several galaxy candidates at redshifts above 7 that, if confirmed, would have stellar masses of 10 to the 10 to 10 to the 11 solar masses. The photometric estimates of the masses were uncertain because photometric mass estimates depend on assumptions about the stellar populations and can be biased. The spectroscopic follow-up, using NIRSpec to measure precise spectra of these galaxies, has begun to confirm the high masses, though the uncertainties remain significant. The most dramatic early report was a 2023 paper using Webb data that claimed to have detected 6 massive galaxies at redshifts above 7, with masses that were, the authors argued, inconsistent with Lambda-CDM. The paper attracted enormous attention and was widely reported in the popular press with headlines like, "Webb has broken cosmology." Subsequent analysis showed that the mass estimates were too high due to modeling assumptions, and the masses of the galaxies were revised downward. The revised masses are still higher than Lambda-CDM expects at those redshifts, but not catastrophically so. The current state of the massive early galaxy problem is that there is a genuine tension between the Webb observations and the Lambda-CDM predictions, but the tension is not fatal. It is at the level of several sigma, not orders of magnitude. The specific modifications to the Standard Model that could resolve the tension include changes to the star formation efficiency, the initial mass function of early stars, or the properties of dark matter halos in the early universe. None of these modifications has been confirmed, but all are within the range of what is physically plausible. This is the second surprise from Webb that is specifically new and specifically relevant to the true size of the universe. Webb has found that the early universe was more complex and more massive than expected. The galaxies at the edge of what Webb can see are not primitive precursors to the mature galaxies we observe nearby. They are already complex, already massive, already structured. The universe assembled its large-scale architecture faster than we thought. The true size of the universe is not just its extent in space, it is its depth in time, the complexity it could develop and has developed in the first fraction of its history. Galaxies with stellar masses of 10 to the 11, solar masses at redshifts above 7, meaning when the universe was less than 800 million years old, Some of these galaxies are as massive as the Milky Way, which has had 13 billion years to assemble its current mass. These early galaxies had less than 800 million years. The specific measurements that reveal these masses come from Webb's near-infrared spectrograph, which can spread the light from individual galaxies into spectra and measure their redshifts precisely, their star formation rates, their stellar populations, and their chemical compositions. The spectroscopic confirmation of high redshift galaxies is one of Webb's most important contributions. Before Webb, high redshift galaxy candidates were identified photometrically from their colors in broadband images. Webb's spectrograph has confirmed many of these candidates and measured their properties precisely. The massive early galaxy problem is not resolved. Several explanations have been proposed. The initial mass function of early stars, the distribution of stellar masses at the time of formation, might have been biased toward more massive stars, which are more luminous and would make early galaxies appear more massive than they are. The efficiency of converting gas into stars might have been higher in the early universe, allowing more stars to form in a given time. Dark matter halos in the early universe might have had different properties than the standard model assumes. None of these explanations has been confirmed, and some require modifications to the standard model that are in tension with other observations. The second major surprise from Webb is the structure of the earliest galaxies. In the standard picture, the first galaxies should be small, irregular, and chaotic. The hierarchical assembly process should not have had time to produce the ordered structures, the spiral arms and bars and elliptical shapes that we see in mature galaxies. Webb found that some galaxies at redshifts above 5 in the first billion years of cosmic history already have disk-like morphologies. One galaxy found by Webb at a redshift of approximately 4.4 already shows a distinct spiral structure, visible in Webb's infrared images with a clarity that no previous telescope could achieve. This is surprising. Spiral structure requires specific conditions of angular momentum, gas dynamics, and the absence of major merger events that would disrupt the disk. Forming a stable disk in the first billion years of the universe, during a period when galaxy mergers were extremely common, is not easily explained by the standard model. These are the discoveries that make the terrifying size of the universe more than just a number. Webb is not just mapping the extent of the observable universe. It is finding that the early universe, the universe in the first billion years, was more structured, more complex, more organized than the standard model predicted. The universe is not just larger than we thought, it is richer, earlier, and more complex. Let me now take you to what I think is the most important and least discussed aspect of what Webb's observations reveal about the true size of the universe. The observable universe, the 46 billion light-year sphere, is the universe we can access with any electromagnetic signal. But there is another horizon, beyond the observable horizon, that defines the universe we will ever be able to interact with. This is the cosmic event horizon that I described in the previous video on the expansion of the universe. The cosmic event horizon is currently approximately 16 billion light-years away. Galaxies beyond the event horizon are receding so fast that any signal we send toward them now will never reach them. Any signal they send toward us now will never reach us. The cosmic event horizon is the boundary of the region with which we can ever exchange information in the future. The observable universe at 46 billion light-years is larger than the event horizon at 16 billion light-years. The difference is the region we can see, but cannot interact with. Light from galaxies at 30 billion light-years has had time to reach us, so we can see these galaxies. But any signal we send to them now will never arrive. The expansion is carrying them away too fast. We can observe them, but never interact with them. As the dark energy drives the acceleration of the expansion, the event horizon stays approximately constant, while the observable universe continues to grow very slowly as light from more distant regions finally arrives. The region we can see is growing. The region we can interact with is shrinking. The two horizons are converging on a final state in which the only galaxies we can see are also the only galaxies we can interact with, a small cluster of locally bound galaxies surrounded by an ever-expanding void. This is the terrifying size of the universe. Not just its current extent, which is 93 billion light years across, but the direction of its future toward isolation, toward the permanent recession of most of the universe beyond any possibility of contact, toward a final state in which the gravitational remnants of the local group are all that can be known. James Webb is observing the universe in the era when it is most accessible, when the most distant galaxies have had time to send us light, when the event horizon is as large as it will ever be relative to the observable horizon. In the far future, the universe will be less knowable, not more. The window that Webb is exploiting, the window of cosmic accessibility, is the largest it will ever be. The terrifying true size of the universe is not just how large it is now, it is the direction it is going, toward an isolation so complete that the majority of what currently exists will become permanently inaccessible. The universe is growing, and most of it is growing away from us, past the event horizon, into the permanent darkness of causal disconnection. James Webb has shown us the edge of what we can see. What lies beyond that edge, including the trillions of galaxies that are already beyond the event horizon and the potentially infinite extent of the total universe, is the true size of what exists. And nothing we can ever build, no telescope, no signal, no technology, can close that gap. The size of the universe is not just large, it is unreachable, and getting more so by the second. I want to close with what I think is the most important and least discussed aspect of what Webb's observations reveal about the true size of the universe. Before I do, let me try one more time to convey the scale, because I am not sure any description so far has fully succeeded. The most distant thing you can see with your naked eye under dark skies is the Andromeda Galaxy. It appears as a faint smudge in the constellation Andromeda, roughly the apparent size of the full moon, though much fainter. Andromeda is 2.537 million light years away. The light reaching your eye tonight left Andromeda when your ancestors had stone tools and were far from anatomically modern humans. The entire span of recorded human history, from the first writing in Sumer to this present moment, is approximately 5,000 years. The light from Andromeda has been traveling for 500 times longer than the entire span of recorded human history. Now consider that Andromeda is at 2.537 million light years out of the observable universe's radius of 46 billion light years. Andromeda is 0.005% of the way to the edge of the observable universe. It is essentially at our front door. The vast majority of the observable universe is beyond what you can see with your naked eye, beyond what Hubble could see with 10 days of observation, in some cases beyond what Webb can see in a reasonable exposure time, and the observable universe is the small part. Beyond the 46 billion light year edge, there is more, much more, perhaps infinitely more. The ratio between the observable universe and the total universe is at least 1 to 15 million in volume, probably far larger, and possibly 1 to infinity. What James Webb has revealed is not a view of this infinity. No instrument can reveal an infinity. What Webb has revealed is the clearest possible view of the finite observable part, and the clearest possible evidence that beyond it, the universe continues without boundary in any direction we can look. The terrifying true size of the universe is not just how large it is. It is how much of it is permanently beyond reach, not beyond current technology, permanently beyond any technology, because no signal can travel faster than light, and the expansion is carrying most of the universe away from us faster than light can follow. The universe that exists is incomprehensibly larger than the universe we can ever know. James Webb is the most powerful telescope ever built. It has shown us galaxies from when the universe was 290 million years old. It has sharpened our picture of the early universe in ways that are forcing us to revise the standard model. It is the greatest tool for cosmic exploration in human history. And it can see the small part, the small, accessible, near part out to 46 billion light years. The rest is beyond reach. Not beyond Webb, beyond anything, forever. If this changed how you think about the universe revealed by James Webb, if the true size of the observable universe and the unknowable extent of what lies beyond it feels different after understanding the physics of horizons and expansion, tell me in the comments. Tell me whether the massive early galaxies found by Webb change how you think about the standard model of cosmology. Tell me whether the idea of an infinite universe with copies of you somewhere in it disturbs you or excites you, and what the difference is. And subscribe if you want to stay at the frontier where the most powerful telescope ever built is revealing a universe that is larger, earlier, and more complex than anything we expected.